So these are the main types of compounds. Right, let's see if I can get this to work again. The first type we're going to look at are covalent compounds. Covalent compounds, as I mentioned, are nonmetal elements bonded to other nonmetal elements. So a nonmetal with a nonmetal usually makes a covalent compound. The elements bond by sharing electrons, and the electrons have a negative charge, and they are attracted to the protons in another element. And this causes many attractions, which cause the atoms to bond together with the electrons being shared. They form molecules, so the definition of a molecule specifically has to do with covalent compounds. One exception is anything with an H in front of it. H in front of the formula and mixed with water is called an acid. So if you see an H and it is mixed with water, you can pretty much predict that it will be an acid if the H is in the front of it. The second exception is anything with ammonia, NH4 in front of it, is ionic, not covalent. NH4 is a polyatomic ion. It does not have any metal in it, but it is a positive one charged ion. And so it forms ionic compounds, not covalent. So those are the two exceptions to nonmetals with nonmetals. Yes?
The exception number one is H2O2.
That would be what it means. H2O2 is a unique one because H2O2 happens to be hydrogen peroxide. But H2O, for example, could even be in that classification. When you just have hydrogen and oxygen, it tends to be a little bit different. But if you have HCl, for example, or HNO3 or H2SO4, many of them with H's in the front are acids. Not all, but in general, we will be focusing on using that to start off. H2O2 and H2O are both kind of exceptions, and maybe they are acids, maybe they are not. Those are other questions looking at acids. Yeah?
So it would be an acid instead of...
It would be an acid instead of a covalent compound. So let's see if I... Come on. So binary compounds. A binary compound is composed of just two elements. Okay, binary means it has so just the word binary means there's two elements. To write the name of a binary covalent molecule, you write the name of the element that is first, that is on the left side of the formula. Most metallic element is usually listed first. It's not going to be a metal, but it's the one to the left of the periodic table. Then you're going to want to write the name of the element that is second in the formula. The last thing you do is you apply the suffix IDE to the second name. So first element, second element, and then apply IDE to the second name. You want to minimize the syllables as much as possible when you add this IDE. So you may be taking out some of the original name of the second element. The last thing you do is you apply prefixes to denote the subscripts. In a binary covalent, it's how many there are. You use prefixes. You do not apply the prefix mono for the first element in a binary covalent compound. The prefixes they use for binary covalent compounds, 1, is mono. You don't use that on the first element, but if you have a one of the second. Second is di. Good prediction. Third is tri. Okay, so mono, di, tri. That seems to make some sense. The fourth one is the weird one. Doesn't seem to fit in. Fourth one is a weird one called tetra. Tetra. It is the one that's kind of different, but it's the basis of much of chemistry. Fifth one is penta, like the shape. Sixth one is hexa, and then you got hepta, octa, nona, and deca. So, a brief way to review binary covalent compounds is you write the name of the first element, the name of the second element plus IDE, and then you apply your prefixes to both of them as needed. So let's look at an example. Okay? Knowing about how it works and making it work, we want to make sure we can look at an example. So, the first one, let's look at the first element here. Okay, C, what element is that? Carbon. Carbon. So, first thing we can write here is we've got carbon. Next element is oxygen. So we start out with oxygen. We may want to have an eraser or a pencil when we do this, because we know we have to add what to the end of the oxygen? I. So, we know there are two oxygens, so we put the di-oxygen in front. And then we change it to carbon dioxygenide. Sounds a little bit off. We got too many syllables. So we got to take the syllables out, and that's why it becomes carbon dioxide. So in oxygen, you take out a whole lot of oxygen, to be honest. Okay? That's carbon dioxide. Next one. First element, N, is nitrogen. So write nitrogen down. Okay. Next element we know is chlorine. And we can do it in the order we want. Dinitrogen, because we got two of those. We got our chlorines. What prefix goes in front of the chlorine? Tetra. And then the chlorine cannot stay chlorine. It has to turn into chloride. Very good. So not chlorinide, sorry. Too many syllables. Change the chlorinide to chloride. There you go. So if it ever sounds a little funny, sometimes they do no matter what, but the extra syllables, that's dinitrogen tetrachloride. So what I would like you to do right now is, you can do this on your paper, please write the name or formula for the following compounds. It's a weird one. Yes, it does. Let's check our answers for these first three. First three here. First one, triphosphorus decoxide. Second one, what do you think it is? Nitrogen monoxide. And the next one, there were two eyes. Yes. All right, I'd like you to put the formula for these three. Formulas usually are easier, but you do have to look at the periodic table. You're more than welcome to use your planner if you haven't memorized most of the elements. If you'd like a list of all the elements you should memorize, I'll pull one up for you. You're given the periodic table like that. You're not given any of the names. The element is bromine. English and American are very different. Legally, the naming of some of these things we look at today, internationally, even if the English pick something else, so they think they're better. Why we split off from that? All right, raise your hand if you've got number 6, number 5, number 4. All right, so keep your hand up if you want to tell me 4. Answer to 4. Yes? XEF sub 4. Woohoo! Nice job. Number 5. Yes? ER3 O sub 8. Excellent job. All right, rocking. And over here. Ooh. What's the L look like? Very good. C2CL6 is correct. So this is how we name binary covalent compounds. Now, there are special cases. So, first special case is ammonia. Ammonia's formula is NH3. If you named it according to binary covalent compounds, it would be nitrogen trihydride. However, it is usually referred to as ammonia because that is its common name. This is another common molecule that has its own specific name, known as carbon tetrahydride. It's called methane. Carbon tetrahydride because it has 4 hydrogens, but methane is what it's known as.
Is that only in America?
No, around the world it's a common name. Yeah. You could still use binary covalent rules for these two, but people would kind of laugh and go, what are you talking about? But same thing with water. Water is another common one. Water has its own name. It could be called dihydrogen monoxide. Sounds cool. It does. All right, so if you want something fun to do, look up that on the internet, dihydrogen monoxide. There's a whole article about how dangerous it is. Now, this is acetylene, C2H2. And last common, this is extremely common, especially in organic chemistry, C6H6 is not named by the binary covalent system. Usually it is called benzene. And it makes what's called a ring structure in terms of its shape. All right, so some special cases. Next class of compounds are ionic compounds. So in your notes, for ionic compounds, it's a metal element bonded to a nonmetal. Metal and nonmetal makes ionic. A ionic compound is a neutral compound which are formed when cations and anions come together in ratios that balance the positive and negative charges, or neutralize the positive and negative charges. Same amount of positive comes together with the same amount of negative. They are called salts. Sodium chloride or table salt is just one of these salts. anything with a cation and anion that balances out its charge is called a salt, or an ionic compound. They form what are called formula units, not molecules. The reason they form formula units is because, like salt's case, for example, table salt, NaCl, the NaCl has a repeating pattern of sodium and chloride ions connected together. A water molecule does not have that pattern. A water molecule can be by itself without any other water molecules attached to it. But sodium chloride and other salts, they form formula units. That's the lowest ratio of that salt, the lowest possible ratio. So NaCl is never found in nature by itself, just Na and Cl hanging out. Instead, it's Na tons of them with Cl tons of them. But the formula is the simplest. The formula unit is the smallest representation unit of an ionic compound. So the smallest representation. Yes, sir?
What's the difference between a formula unit and the empirical formula?
An empirical formula is usually specifically applies to molecules, but an empirical formula is the simplest formula of a molecular compound. So benzene, for example, was C6H6. That was one of our specialty examples. C6H6 here. And if you simplify this to the simplest formula, this would be, there's a 6-to-6 ratio, so this would be its simplest formula, which is called its empirical formula. This is what is called a molecular formula. Now, that's usually dealing with molecules and their simplest formula. This CH isn't found in nature, but this benzene is. So, it's not always the case. Sometimes an empirical formula and a molecular formula are the same. But a formula unit, just like an empirical formula, is the simplest ratio. However, in ionic compounds, it's the only ratio you can write. You can't write Na5Cl5. That would not be an acceptable result. Now, additional ions lead to the formation of crystals. So as more and more ions come together, it makes a larger structure called a crystal. On the very next page, we have a picture of a crystal. This is an NaCl crystal. On D, you see it has a large, clear structure. And then E shows the separation of the Na and Cl together in this sodium chloride structure. It forms a cubic structure for this particular salt. Different salts have slightly different crystal structures. So you can see here, the Na is surrounded by 8 different Cls. Yes?
What would the formula unit be? Is that whole, like, E with all the Cl's and Na? Is that whole thing formula unit?
The formula unit is NaCl only.
But I thought you said they only not just like an Na and Cl. Like,
Correct.
you need a bunch.
Yep.
That's the whole thing was.
The way it's written, the formula unit shows the ratio between the two. So you have a ratio of NaCl. That is the way the formula for an ionic compound is always written. If you actually spent the time trying to count these individually, which we will talk about why that's not a good idea, but if you had like 1,000 NAs and you had 1,000 CLs, okay, and you wrote this as a formula for a salt, this would not be an acceptable formula. It is always one of these and one of those. So you can't alter it by adding these here. With molecules, it's a different story. With ionic compounds, this is the formula unit, the simplest ratio. Does that help? Simplest ratio. Just NaCl in this case. Now, comparing molecular and ionic. This is an example of a molecular compound. This is propane. It contains individual C3H8 molecules. You'll notice it happens to be a gas, but all of these are separate from one another. Table salt contains an array of Na plus ions and Cl minus ions. One of the positive and one of the negative make the formula unit. So NaCl comes from an Na and a Cl ratio. So every Na you have to have a Cl, otherwise it is not neutral, it's not balanced in its charge. The rules for naming ionic compounds. First, you want to write the name of the cation, the metal. The cation is usually listed first in an ionic compound. Then you want to use the anion as a guide to determine the cation charge. Now, cations, what's the charge on a cation? What about anion? Negative. So, you're going to be using the anion, or the negatively charged ion, to determine what the positive charge is on the cation when you have a formula. You're trying to determine its components. So, you can use either the stock name or the Latin name. Stock name or the Latin name for these. We will usually be using the stock name, but Latin names still are acceptable, just not used as much. You're going to write the name of the anion, the nonmetal. So first you write the cation, you figure out its charge, then you use the stock system to write its name, then you write the name of the anion. And anion names already have special suffixes. So you do not have to change the anions if you have them memorized. Right now, the anion name is still preferred. There are some, the International Committee is talking about having a standard system because there's still some debate on how this is set up and this is set up. In the next few years, they may, they will add a little bit more to this naming process. But right now, we don't have to worry about that. Not until next year, maybe when you're in college. So I'll show you that later. Do not apply prefixes to donate subscripts. Cations and anions bond together until the total charge is 0. You'll notice that is in bold and underlined. Probably the most important thing about ionic compounds, naming and formula writing. So the first thing to look at is formula. How do we get a name from a formula? So to get a name from the formula, we start out, according to our rules, with the name of the first element, which is the cation. So Ca is the cation here. Its name is calcium. The next thing we do is we look at the anion, which is chloride. The INE changes to an IDE in the ionic naming for a single atom ion. When you get to polyatomics, there's some different ones. So they have slightly different endings. But for single atoms ones, yes. Now, if you put calcium here and chloride here, you've got 2 chlorines, 2 chlorides. So convention would say you'd put a di in front of it. However, you don't want to put a di in front of it. The binary covalent are the ones that have prefixes. If you're not binary covalent, you don't have a prefix. The reason why is calcium here has a positive charge. Calcium here has a positive 2 charge, and chlorine, with its position on the periodic table, has a negative 1 charge. This is why we need 2 of these chlorines to cancel out the positive 2 charge of the calcium. This is the only way you would find chlorine and calcium together. You would never find calcium trichloride because its formula wouldn't be neutral. It would not be balanced in charge. For this one over here, NH4 is ammonium, PO4 is phosphate. And that's all you need to do to name ammonium phosphate. The fact that there's 3 ammoniums has to do with the charge. phosphate happens to have a -3 charge, ammonium happens to have a +1 charge. That's why you need 3 ammoniums to make it neutral. But once you have the formula, if someone gives you the formula and says write the name, all you have to do is find the 2 items that are located in it. Yes?
For the first one, the only reason it's chloride is just because you just memorize that. Cl2 is chloride. Or
Anytime you have a binary, we have 2 elements only. So we got calcium and chlorine only, 2 types of elements. That's called binary. If it's binary, it ends with an IDE. So that's a rule for binary. Yeah.
alright.
Yeah.
So then, how would you tell the difference between naming between the two?
Great question. How do we tell the difference between naming between binary ionic and binary covalent? Right? So the cool thing is with this, let's see that. Easy to. So for binary compounds, that means there are 2 different types of elements in it. To know the difference, all we need to know is the periodic table. Oh, there we go. Doesn't matter how poorly you draw it. On this side of the periodic table, on the left side, I'm not even going to look at the bottom. Right now are the metals. On the right side are the non-metals. And in between the stair step are the transition metals. For knowing what type of chemical bond or naming you use, there are 3 different options. You can have a metal with a metal. If you have a metal with a metal, this makes what is called a metallic bond. The great thing about this is we will not learn how to name them. They have their own classification. But just so you know, if you have all metals together, metallic bond. So, the next type is a metal with a non-metal. This makes what is called an ionic bond. So an example of this, sodium chloride, is a great example here. Third type is if you have a nonmetal with a nonmetal. And this is classified as a covalent bond. For naming, we're going to look specifically at what are called molecular covalent. Molecular covalent, they are molecules. And we learned how to name what are called the binary ones, which mean you have 2 types of elements in it. Now, H2O is one of those, but its common name is water. But I will use that as an example. Dihydrogen monoxide is one type of molecular covalent compound. Now, since ionic compounds, they have two different types. The first one we looked at just in the previous slide was what's called a binary ionic compound. Just like a binary covalent, it has 2 types of elements. Now, how do you know it's ionic and not covalent? You look back at the elements that are found in it. And that's all you need to do. Does that make sense? Now, so that's binary. When you have more than 2, sometimes this is called ternary. It's just a name to describe you got a polyatomic ion in there. Okay, it's not binary. So when it's not binary, that's where the ion sheet helps out in memorizing that. So for the, yes?
For the first one, how do you know that calcium is +2?
Very good. Calcium. Calcium is +2 based on its position here in the periodic table. Okay. A general way of knowing some of the charges on the elements on the periodic table when they become ions is here, if you're in group 1 here, these elements here tend to lose 1 electron to become an ion. So if I went to sodium, for example, sodium has 11 total electrons in a neutral sodium. If it loses 1, it goes from 11 to 10. When it loses that 1 electron, it now has the same number of electrons as neon, which is called a noble gas. Noble gases tend to be much more stable and less reactive. So the general pattern is this tends to lose 1 electron and becomes a positive 1. These tend to be positive 2, positive 3. And then over here, F wants to gain 1 to be like this. So it's negative 1 here for the halogens, negative 2, and negative 3 in general. So that is the pattern. Yes?
How do you know the suffix for the ion?
For the what?
For the ion, like how do you get the suffix?
For the suffix here, there are some rules for the suffixes, and we're going to look at that in just a minute, why it's phosphate and not phosphite or something like that. We will look at that right now, where that comes from, as we go. So hopefully we'll answer those. Yeah?
These are gain electrons if it has 4 valence electrons.
4 right here. The 4 ones, depending on which one we're talking about, all of these here that are metals tend to lose electrons, and carbon can gain electrons and form what's called a carbide ion, which is carbon 4 negative. Yes?
When you said it goes for binary ionic,
Uh-huh.
it goes I. Did you mean when it's like CaCl, that's 2, or did you mean Cl2, or like Cl2?
If it was NaCl, NaCl would be sodium chloride. CaCl2 is calcium chloride. MgCl2 is also going to be magnesium chloride, pardon me. So it doesn't matter how many of these you need to make it neutral. It's just what's in it. You don't need prefixes. You don't need to designate how many there are in the name. So that's the nice thing about ionic compounds, is that when they're binary, they always end in IDE, makes it easy. And then when they are polyatomic, they are based on a set of rules that we're going to look at in just a moment, but there is general names you can see on your ion sheet. Now, this is the third case. This is a binary ionic. This one here is ternary. This one here is also ternary, and it contains iron. Iron is a transition metal, and transition metals and some other elements, sometimes they have the ability to lose a different amount of electrons. So they have an ability to form different types of ions. The BrO3 is known as the bromate 5 anion. The challenge with iron, though, is once you know that iron is in it, there are 2 different common ions of iron. Iron 2 plus and iron 3 plus. Iron tends to lose 2 electrons or lose 3 electrons. So it can become a 2 plus or 3 plus ion. So the thing is, we now need to figure out which one it is based on the anion. So we look at our anion, which is BrO3, 1 negative on our ion sheet. There are 3 of them, so what is going to be the total charge on the bromates?
3.
All 3 of them together would be -3 or 3 negative. We've got 3 of them there. That means that the iron for the 3 positive charge will be the only iron that could be with this bromate. So this is iron 3 bromate. The 3 is a Roman numeral meant to represent the charge on that ion. So this here, this Roman numeral is for the metals. When the metals have more than 1 possible ion choice, that's why they use the Roman numeral. They can also use the Latin name for this. So iron 3 bromate And iron 3's Latin name is ferric, so that's another name that could be used to describe the exact same thing. Yes, sir?
Why does bromine have a 5 when it's started?
Very good. Bromine has a 5 because as an anion, it has to do with how the electrons are arranged around this bromine and oxygen group. Because these here are all nonmetals, they are sharing electrons. And as they share electrons, they need one additional electron to make it a stable structure. Because of that, it's what is called oxidation state. That's why the 5 is there. But this here, the iron 3 bromate, is the way it is commonly written. And this is what we'll be using in this class here, is we will not be using many times the Roman numeral after the second one. That's common. Yeah.
For the AP test, would we be finding iron 3 bromate, or would we have to know ferric or ferric?
You will have to know this here, the AP test. This here, I'll be honest, I don't really remember the ferric or ferrous, but you may need to be aware of it in terms of everyday use. I do not believe that they switch between them. I will double check that though, because they may have changed it. Now, once you can get from a formula to a name, the next step going from a name to a formula does involve more of making sure it is neutral in terms of its ionic charge. So if we take the name of one of these here, this is lithium phosphide. The first thing we need to do is find out what the charge is on lithium. So lithium happens to be right here on the periodic table. It's in what group on the periodic table? 1. So it tends to want to lose 1 electron, which means it will have a charge of 1 positive. Phosphide. What group is phosphide on in the periodic table? 5. So, the way I remember that is if I look at the phosphide, or what's phosphorus right now, in order for it to become phosphide, it has to gain 1, 2, 3 electrons. And are electrons negative or positive? The electrons are negative. The electrons are negative, so that means it is going to gain a 3 negative charge. So phosphide would be P with a negative 3. It's also written second, which gives it away that it's got to be an anion. It has to have a negative charge. But that is lithium and phosphide. Now, if we look at these two here, is that neutral right now? Nope. You got 3 negatives and 1 positive. So what you need to do is make sure that the charge is neutral. Add another lithium ion. Now it's 2 plus. Add a third lithium ion, and now you've got 3 positives and 3 negatives. That would be your formula for lithium phosphide, Li3P.
So you don't, actually write the formula, you don't put any letters.
I know, the formula does not have a charge written on it because it is neutral. If you really wanted to, you could write a 0 up here, but that's usually only done for metals.
So, I didn't write the individual charges.
You do not write it, no. You have to erase it if you do write it to figure out its formula. Yeah, you erase it when you're showing the actual formula. Yes?
Just out of curiosity,
Yeah.
are the subscripts usually on the metal or the non-metal?
Could be either or. Yeah, there's no common convention to it. But let's try another one. Calcium nitride. Let's look at calcium. Okay. Predict what the charge on calcium would be. Daniel? Daniel? Not really. It's funny. A chemist will grade a free response question, and all they have to do is put bullets. You do not have to write an essay. The more you write, the less you read. So it's different. You have to clearly communicate, but you can do it in bullet format. Chemists are a much, in terms of grading in the exam, that's what my friend who's been grading exams 15 years, she told me. She said, yep, short and sweet. You can just, sometimes you can just show your work and you have no words at all. All right, calcium. Nitride. What's the charge on nitride? 3. So the formula, we need an additional calcium. We add one more calcium, doesn't make it. Add another nitrogen. Nope, that kind of messes things up. Add another calcium. Oh yeah, we're good. There we go. Ca3N2 is calcium nitride. Clarifications on this one here? Now, one way of doing it is by drawing out beautiful pictures like you just saw. Another way is what is known as the Criss-Cross Method. This is not from the 1980s or 1990s, but lithium phosphide. How would you do this with crisscross? All you need to know is the charge on the ion. You take the charge on the first ion and put the number on the second ion. Take the charge on the second ion and put the number only on the first ion. That's crisscross, that's it. The only time this will not work is if you get a ratio of like 2 to 4, and you have to simplify it. So you might get something like lead-4 oxide. Here's an example of something that wouldn't work, but it's really not that hard. If you had lead-4 and oxide has a -2 charge because it's in group 6. Wants to gain 2 electrons. You can crisscross this and you get Pb2O4. But now you have to simplify. If you said this, it would be 100% wrong 100% of the time. So you just write PbO2. That is lead-4 oxide. That's the only case it doesn't work in ionic compounds. And you remove the 1. You remove the 1. I'm sorry, I didn't say that. Remove the 1 from the P because it's implied that the 1 is there if you write P. So let's try calcium nitride. You can see quickly. +2, 3-, crisscross. Should be the Ca3N2, same formula. Okay. So that is usually a little easier. Let's try strontium nitrate. I'm sorry, strontium nitrite. Pardon me, I said it wrong. Strontium is number 38 on the periodic table. Only time it doesn't work is when you pull out for ionic compounds is when you need to simplify. If it's a whole number ratio that can be reduced. The formula unit is always the least smallest whole number ratio. So it's awesome. I can't say it always works because if you just use it and you don't do the next step, you're out of luck. Yeah. That's the only way to know. It's a lot of language. All right, strontium nitrate. SR is 2 plus. Nitrite is NO2 with a 1 charge, negative 1 charge. Now, when you crisscross this, you got the SR with another 2 there. You got the nitrite with the 1 there. And now it's a question of how do we show this? SrNO22 doesn't quite work so well. That means you have 22 oxygens and 1 nitrogen and 1 strontium. So instead you use your parentheses to show it correctly. Parentheses around the NO2, that's the nitrate ion. There's 2 nitrate ions for every 1 strontium ion. The cool thing about this is, this has a negative 1 charge. This has a positive 2 charge. Chloride ion has a negative 1 charge. If I had strontium and chloride, it'd be SrCl2. Anything that has a negative 1 charge would form the same formula with it. 2 of these to 1 of those. This just happens to be a group of atoms working together as a single ion, called a polyatomic ion. Now, watch out for hydroxide. Strontium hydroxide. Sr, what's its charge? 2 plus. Hydroxide, looking at the ion sheet. Hydroxide. It's an anion. Okay, OH with a minus. 1 minus or just a single minus is commonly written. Reasoning why. Because it's non-negative. That's the best way to explain it, non-negative. H is sometimes written in the front when it's usually an acid. And we'll talk more about that. But when it's OH here, it is not an acid. So if we switch these two, this is a big problem for all chemistry students. Because if you write this as the answer here, you're wrong 100% of the time. Because guess what's in here? H2O. This is saying that it's strontium with water. And even then, it can't be that. Water and strontium actually react when they put together. It's a whole other story. So it can't do that. It's not a hydroxide anymore because you did not distribute this properly. So you need to use your parentheses once again. Fail. Real bad. Yeah, no good. So fix it. Success, we're happy. Yeah. All right. At this time, I'd like you to write the name for the following ionic compounds. Again, if you don't know the name of a symbol, you are more than welcome to use resources to help you figure out what they are. In your lab manual, there are some periodic tables with more information in the back. Always will when you have a binary. This oxygen is changed to oxide. And this here is what All right, for these ionic compounds, let's check our answers here. We got sodium nitride, tin 4 oxalate, also called stannic oxalate if you like the Latin system. Barium peroxide. A peroxide. It has to do with the charge on the barium. Okay? Barium has a positive 2 charge. Oxygen, there's 2 of them. So barium has the positive 2. Oxygen here, if you had 2 of them, its total charge would be negative 4. That does not cancel out. So you cannot have the negative 2 charge on the oxygen. The other option for oxygen, okay, is O2 as a whole has a negative charge, and that's called peroxide. So on your ion sheet, peroxide is an ion that is different than oxide ion. It is O2 negative, O2 2 minus, O2 2 minus, and oxygen by itself is just O 2 minus. The difference is there are two different ions. All right, let's move on to looking at the next step. So next step, you're going to take a name and write the formula for these 2 compounds here. Balance out. You only have one oxalate. Different compound. You can't have this. It has to be. It's not neutral. All about being neutral or being balanced, if you want to call it. done?
Linux can have a host.
These two done? All right, we got about 50%. 50% rule applies. We are going to look at these two. If you're not part of that 50%, I would suggest either finishing them right now or being quiet. Your choice. Bismuth. What's the charge on bismuth? All right, so we got 5+ on that. And carbonate? 2-. And its formula is? Carbonate. So if we look here, we do our Criss-Cross Method. Should be Bi, CO3, and there's our bismuth 5 carbonate. So, yes? Yeah, bismuth can form different ions. This one here, you see the 5 here, Roman numeral 5, that's what tells you it's a 5+ ion. What's up? It's yellow? It's supposed to be green. Doesn't like doesn't have red. All right, looking at these here, the ferrous thiosulfate is one you do not need a parenthesis because there is only one thiosulfate and they neutralize one another. You do need parentheses around this because you need to have 3 of these to neutralize the aluminum, and you have to have parentheses around your hydroxide, otherwise you get water and you get the wrong failed answer. So, any questions, clarifications on this right now? This is how to make ionic compounds, yes sir?
For the thiosulfate, you need to put parentheses around the S2 and the O3.
No, you do not, because there's only one of them. So you never put parentheses around it when you have one. When you have more than one, then you have to if there's multiple atoms, polyatomic ion. Now, some unusual ions. Mercury. Mercury 1 exists only as Hg2+. 2+. Okay? It's a unique ion. The peroxide and oxide is kind of unique as well. It's kind of weird. Why does it do that? It's more confusing than we want it to be, but that's just the way it is in nature. There is Mercury 1 and Mercury 2. Mercury 2 exists as Hg2+. The thing about this is it looks almost opposite. But Mercury 1 has to do with its charge. The Roman numeral always has to do with the charge, not the number. So, Hg2+, that means you got 2 Hg's. Each individual Hg has a 1+ charge on it, so to speak. But it's only found together, so it's not Hg just with a 1+, which, again, is unusual. This is another unusual ion. This is known as the acetate ion. C2H3O2, 1-. Acetate is very nice because people often write it, especially in organic chemistry, as ethanoate. These are exactly the same thing. It's just written in a different form. This is written as CH3COO with a 1- charge. So it has 2 names, same formula, same chemical composition, everything about it is the same. Just organic chemists like to write it with this coolness on it, without the L at the end. And there's a reason for it, but...
Are they used interchangeably?
Yep, they can be used interchangeably. I use acetate more often because I'm not as organic as some people. But ethanoate, if you like organic, you can use ethanoate all you want. Now, the cool thing is, when you look at your ion sheet, you'll notice that there are a lot of things that have names that are similar, but the endings just change a little bit. These are the 8s and the ites. For example, chlorate. Chlorate can have multiple different amounts of oxygen. Chlorine with oxygen is referred to as a chlorate. Now, this with the Roman numeral here is a system that will probably be used in the near future. Okay? The names we currently use are usually the hypochlorite and so on. The very top one, I'm sorry, not the top one, the second to top one is called the chlorate. The chlorate ion has 3 oxygens around 1 chlorine, and it has a 1 negative. Everything is based off of the chlorate. So, if you have more oxygens, it is a per state, or a hyper state. More energy is hyper. Per state is the ClO4. 1 more oxygen is per. 1 less oxygen than the 8 is the ite, chlorite. It has 2 oxygens. 2 less oxygens, or 1 less than the chlorite state, is the hypo, or low state. Hypo meaning low, hyper meaning high. Those are the, again, the roots of the prefixes. And again, the Roman numerals here. 8 is the default version. Ite is 8 minus 1. Hypoite is ite minus 1. And per 8 is 8 plus 1. The oxygen, it will always have the same charge on all of these. Yes? These actually refer to what are called the oxidation numbers, and it has to do with how the electrons are being shared around these polyatomic ions. We will focus on where that comes from in the future. Right now, all you need to know is this name is the same as that name. Okay? So I'm just going to tell you that right now. It takes a little more knowledge of chemistry to know why they are that way. Yep. All right. So if we look at the 8s and ites, let's see if we can fill in a little bit. We got bromate. Bromite would have how many oxygens? 2. Hypobromite, how many oxygens? Perbromate. 4. Very good. Now I'd like you to fill in, oh man, I always do that. Fill in the iodate. The iodate ones that are not filled in for you. Start with iodate. You can use the ion sheet for that. Iodate is IO3 1 minus.
How do you keep the same charge? How does
The next classification of compounds includes sulfur. These are the ones that, when an oxygen atom is in an ion is replaced by a sulfur atom, the prefix thio is added to the name. So just when you replace one of the oxygens with a sulfur, the thio comes in beforehand. So, if this is the cyanate ion, OCN 1 minus, the thiocyanate just has the O replaced by an S. So anytime an S gets in there, it just gives the thio prefix. Sulfate is SO4, 2 negative. If you replace one of the O's with an S, it now becomes S2O3, which is the thiosulfate. So the name's the same, just add the thio. The next category of chemicals that we will most commonly use are the acids. We know H is written first in a formula of acids. There are 2 main types of acids. Binary acids, and what are sometimes referred to as oxyacids or ternary acids. I like ternary, but oxyacids works just great. Oxyacids means you have, again, an oxygen in there, and you've got more than 2 element types in there. The A is usually a nonmetal for all of these acids. The nomenclature is similar to ionic compounds, so the same similar rules and ideas. They have to be neutral. They have to be neutral, just like an ionic compound. Now, the name depends on whether or not the acid compound is dissolved in water. It must be dissolved in water. If something's dissolved in water, it is said to be in an aqueous solution. Oxyacids are the most common acids. This is a binary acid, and then this is an oxyacid here. Those are the most common acids we deal with in day-to-day life. The first rule is for binary acids, if it's in water, it says AQ, or aqueous solution, you always write the prefix hydro. You write the name of the second element. So hydro, and then you write the name of the second element, and you apply ic to the second name. Minimize syllables as much as possible, except, here's our exception, sulfur and phosphorus. So those you do not minimize the syllables. Then at the very end you add acid, just in case they didn't get the fact that you were talking about an acid there. So you have to have acid at the end. Now, if it's not in water, if it's a binary acidic compound, but it's not in water, it no longer has properties of an acid. It's not in water. So all you have to do is write hydrogen and the name of the second element. Then you add IDE to the second name, just like a binary ionic. And minimize syllables as much as possible. Here. So here's an example. Formula to name for this. This is the same molecule. One is in water, one is in the gas phase. If it's in the gas phase, it is not considered an acid. So we start with hydrogen. Sulfide. And that's dihydrogen sulfide because it is, again, an ionic. It's a covalent because hydrogen is not a metal. So that's the thing about, the di is not there. Pardon me, I'm not used to this di stuff put in there. Di is never put in there. Hydrogen sulfide is just the name. It is not covalent. If it was covalent, we put the di in there. Next one is an acid. It's aqueous, so it's hydrosulfur. So hydrosulfuric acid. And that's how to write the name of a binary acid. Nope, no dyes in it at all. It is more like ionic, yes. It is not ionic, but it is more like an ionic mixture. Yep.
Why did we have dye in front of H2O?
It shouldn't have been there.
Why didn't we?
Why didn't we? Because it's not covalent. The hydrogen makes it an acid, so it doesn't fit the covalent rules. All right? Now, for what we are going to do tonight, let me just check on where we're at. We still have a few things to look at with our notes. Let me see if I can get this to work. 41. Okay, for homework.